Now, what's the gradient vector? Well, the gradient of this function, so partial w partial x is 2x, and partial w partial y is 2y. So let's say I take a point x comma y, and I try to draw my gradient vector. So here at xy, so I have to draw the vector 2x, 2y. What does it look like? Well, it's going in that direction. It's parallel to the position vector for this point, and it's actually twice the position vector. So I guess it goes more or less like this. What's interesting to us is it is perpendicular to this circle. Okay? So it's a general feature. Actually, let me show you more examples. Oops, not the one I want. So I don't know if you can see it so well. Well, hopefully you can. So here I have a contour plot of a function, and I have a blue vector that's the gradient vector at the pink point on the plot. So you can see I can move the pink point, and the gradient vector, of course, changes because the gradient depends on x and y. But what doesn't change is that it's always perpendicular to the level curves. Anywhere where I am, my gradient stays perpendicular to the level curve. Okay? Is that convincing? Is that visible? Even for people who can't see blue? Okay. So okay, so we have a lot of evidence, but, let's try to prove the theorem, because it will be interesting. So, first of all, sorry, any questions about the statement, the examples? Yes? Very good question. Why is the gradient vector perpendicular in one direction rather than the other? So we'll see the answer to that in a few minutes, but let me just tell you immediately, to decide which side it's pointing to, it's always pointing towards higher values of a function. Okay, and we'll see that maybe in about half an hour. So, well, let me say actually, points towards higher values of W. Okay. Any other questions? I don't see any questions. So, okay, so let's try to prove this theorem, at least this part of the theorem. We are not going to prove that just yet. That will come in a while. So, well, maybe we want to understand first what happens if we move inside the level curve. Okay, so let's imagine that we are taking a moving point that stays on the level curve or on the level surface. And then we know, well, what happens is that the function stays constant. But we can also know how quickly the function changes using the chain rule up there. So maybe the chain rule will actually be the key to understanding how the gradient vector and a motion on the level surface relate. So let's take a curve, r equals r of t, that stays inside, well, maybe I should say on the level surface. W equals c. Okay. So let's think about what that means. So just to get you used to this idea, I'm going to draw a level surface of a function of three variables. Okay, so it's some surface given by the equation w of x, y, z equals some constant c. And so now I'm going to have a point on that, and it's going to move on that surface. So I will have some parametric curve that lives on this surface. So the question is, what's going to happen at any given time? Well, the first observation is that the velocity vector, what can I say about the velocity vector of this motion? It's going to be tangent to the level surface. Right? If I move on a surface, then at any point, my velocity is tangent to the curve. But if it's tangent to the curve, then it's also tangent to the surface, because the curve is inside the surface. So, okay, it's getting a bit cluttered. Maybe I should draw a bigger picture. Let me do that right away here. So I have my level surface, W equals C. I have a curve on that. And at some point, I'm going to have a certain velocity. So the claim is that the velocity v equals dr dt is tangent to the level W equals C, because it's tangent to the curve and the curve is inside the level. Okay? Now, what else can we say? Well, we have the chain rule to tell us how the value of W changes. So by the chain rule, we have dW dt. So the rate of change of the value of W as I move along this curve is given by the dot product between the gradient and the velocity vector. And so, well, maybe I can rewrite it as nabla W, sorry, del W dot V, and that should be, well, what should it be? What happens to the value of W as t changes? Well, it stays constant, because we are moving on a curve. That curve might be complicated, but it stays always on the level W equals C. So it's 0, because W of t equals C, which is a constant. Okay, is that convincing? Yeah. Okay, so now if we have a dot product that's 0, that tells us that these two guys are perpendicular.